Today will be our first look at continuous probability. So 15 and 16 deal with this concept, but let's start with 15 and have a look at and explore continuous random variables. So continuous random variable is one that can take any value in an interval of the real number line. Continuous variable is often one that is measured such as height, length, and time. So you'll see these commonly come up in stacks and exams. So the height or the wingspan of a bird, the length of time waited for a ride at a carnival, etc., etc. A continuous random variable has no limit as to the accuracy with which it can be measured in theory, but is often limited by the accuracy of the instrument measuring the variable, such as stopwatch or ruler. For example, if you measured how quickly someone ran 100 meters, and I think the record by Usain Bolt, something like 9.53, I'm making that up. But in fact, that wasn't his time. That could actually be measured further and further, but we're limited by the instrument measuring the time it took him. A random variable cannot take an exact value since it's always rounded to the limits imposed by the measurement of the method of measurement used. So we say that his time was 9.53 or whatever it actually was, but the reality is time could be measured much more precisely than that. In fact, infinitely more precise. So the probability density function of a continuous random variable x is a function of x, f of x, with a domain all real numbers. So that's important. So they have a domain. You can throw any number you want into a continuous PDF. So that the probability that x lies between an interval AB is given by the area under the curve. So this is where we start to see integral calculus come into probability of all things. I bet you didn't see that one coming. So in general, for the continuous random variable x with this density function f, so this is f of x here, this is our function, then the probability can be found by looking at the values or the area under the curve between b and a. And this part here, this area, will be the probability that the random variable is between these two values. So just a couple of things to note. A continuous probability density function satisfies these two properties. The first thing is it's above the x-axis for all x values, or on the x-axis. So above or on the x-axis for all x values. So it can't go below. Property 2 is that if you integrate between positive infinity and negative infinity, the area under the curve will always be 1. Now, since the probability that the random variable is a particular value, just say we're looking, just say this value here was 3, right? So probability that the random variable takes on the value 3, we're going to say that that's 0 because if you remember, if we integrate a function, so integrate a function f of x between 3 and 3, the answer is 0. We can't actually get an area at a point. It's got to be between 2 points. And that's why with continuous probability, greater than and equal to is basically the same as greater than. We use them interchangeably. Okay, so let's do a question. Consider the function f with the rule. So it's this between 0 and 1, and it's 0 everywhere else. Let's sketch the graph. So we can see here it's a quadratic function. So we're going to pop 0 into it. 1 take away 0 is 1. 1 times 1.5 is 1.5 or 3 on 2. 1 goes in, and 1 take away 1 is 0, so it's 0 when x is 1. And all that is a parabola that has been moved up 3 on 2. So this is also the turning point. So that's what it's going to look like. So between 0 and 1, we're these values, and everywhere else, we're nothing. So it's just a horizontal line there and a horizontal line there. All right, so show that f is a probability density function. Okay, so the first thing to note is f of x is greater than 0 for all x. Okay, so that's condition 1 met, that the function is greater than 0, or the y values are greater than or equal to 0 for all x. Okay, the second thing is if I integrate between 1 and 0, this area here should equal 1. So that's what I'm going to show you. So I'm going to say 1 equals integrate 1 and 0, f of x, which is 1.5 or 3 on 2, take away 3 on 2x squared for the independent variable x. All right, so let's go ahead and do this. So this is 3x on 2, up by 1 and halved. So that's 3 on 6, which is 1 on 2. So that's going to be x to the 3 on 2. And we're popping in 1 and 0. Let's move the working over here. 1 equals, so let's pop 1 in, which will be 3 on 2, take away a half. Take away, put 0 in, it's going to be 0 in this case. 1 equals, so that's 3 on 2, that's 2 on 2, which is 1. 1 take away 0 is 1, as required. Ooh, RQD. All right, so it is a probability density function. You might think, what about the other stuff? Well, the area under the curve between this part here and this part here is 0, so we don't include that. We don't have to worry about it. Okay, so find out the probability that the random variable is greater than 0.5. So what we're going to do is integrate then. So that's going to be a half there. So what we want is this area here. That's going to be the probability that the random variable is larger than 0.5. Now, remember that greater than and equal to are exactly the same thing. So it could be written like that or without it, and it will be exactly the same move. So we'll start with the top value, which is 1, the lower value, which is a half. 3 on 2, take away, 3 on 2, take away 3 x squared on 2 dx. All right, we know what the antiderivative is already because we worked that out earlier. 3x on 2, take away x cubed on 2 with those terminals. Now we know that when 1 goes in, because we did this before, the answer is 1, so it's going to be 1 take away. So this is, x is going to be half, so this is going to be, let's just work this out. 3 times half on 2, take away a half cubed is an eighth on 2. Run out of working out space. Equals 1 take away. So this is 3 on 4, take away 1 on 16. So that's 12 on 16, take away 1 on 16. So that is 1, let's just write that as 16 on 16. Take away 12 on 16, take away 1 on 16. Mental blank here, 11 on 16. I hope I've got that right. 12, take away 1 is 11, okay? 5/16. So the probability that x is greater than or equal to 0.5 or greater than 0.5 if you want is 5 on 16. Now again, it's pretty easy to do this stuff on the calculator, so we'll run this now on the calc. So grab your integral from Math 2. We got 1 and we got a half, and 3 on 2, take away 3 on 2 times x squared dx 5 on 16. Okay, consider the exponential probability density function f with this rule here. Okay, so sketch the graph of f. So it is an exponential function reflected in the y-axis and not moved up or down. So basically we're going to have an asymptote along here, along the line y equals 0. Let's get the y-intercept, which occurs when x is equal to 0. So e to the 0 is 1. 1 times 2 is 2. And because it's been reflected, what's going to happen, and we're doing greater than 0, so it's hollowed out there. It would swing through and go down like this, but we're only going to take this part of it. It's going to head towards there. And when it's less than 0, or less than or equal to 0, we just got a horizontal line. Okay, so there's our sketch. Show that it's a probability density function. Okay, so the first thing to note, f of x is greater than or equal to 0 for all x. So that's the first condition met. Okay, the second condition is if I integrate this thing here, then it needs to be 1. So 1 equals integral between. Now the lower value is 0, so this is where I'm starting. The upper value, now what's the upper value? Now this is where it gets a little bit tough. So this function here will tend towards 0 as x increases, but it will never actually get there. So I'm actually looking for the area under this curve greater than 0. Where does it end? Well, positive infinity. Now let's pop our function in, 2e to the negative 2x dx. Alrighty, so now I need to integrate this thing here. So what we'll do is get our antiderivative. So divide, which is negative e to the negative 2x. Going to pop in infinity and 0. Now the question is, how do I put infinity in here? Well, what you've got to do is imagine putting the largest number you can think of in here. Okay, so let's just imagine that value there, let's just imagine it's 1,000. All right, so let's go negative e to the negative 2 times 1,000. All right, so that's going to be negative e to the negative, so this is negative 2,000. Now what we'll do is we'll use our index laws to write that as negative 1 over e to the positive 2,000. Now what this is 1 divided by an extremely large number, which is almost 0. Now, as this number infinity, I represented infinity with 1,000. Okay, but if you imagine that gets bigger and bigger and bigger, this will actually just get closer and closer and closer to 0. So we're going to say that negative e to the negative 2 times infinity, that's the first substitution, take away negative e to the negative 2 times 0. Now this one here evaluates to 0, take away. Now this is going to be 0, e to the 0 is 1, negative 1. Okay, and you can see here what's about to happen. 0 subtract negative 1 is 1 as required or as expected. All right, so believe it or not, I can put positive infinity into a number. I can substitute infinity even though I don't even know what infinity is. It's amazing. Okay, find the probability that the random variable is greater than 1. So find some space here. So probability that the random variable is greater than, what's it? Greater than 1. So remember, that's the same as greater than and equal to 1. It means exactly the same thing, so we're not to worry. Integrate between positive infinity and 1. Okay, so that's really what I'm doing there. Imagine that this is 1 on the Cartesian plane. I'm looking for this area here. So upper terminal is positive infinity, lower terminal is 1. Our function is 2e to the negative 2x dx. All right, we know a little bit of this already. So the antiderivative is 2e, no it wasn't. It was negative e to the negative 2x, positive infinity in 1. When we jammed positive infinity in before, we got 0 and nothing changes this time. So let's pop 1 in, and what we're going to get is negative e to the negative 2. So 0 subtract this is just e to the negative 2 or 1 on e squared. So that's our probability, 1 on e squared, 1 over 2.7 squared. Okay. Okay, suppose that the random variable x has the density function with the rule that find the value of c that makes it a probability density function. Okay, so that one there means that 1 needs to equal between 2 and 0 cx dx. So when I integrate cx between 2 and 0, the answer or the area under the curve needs to be 1. Okay, so let's just use this rule that allows me to take that c out times. Now what I'm going to do is anti-diff x, which is x squared on 2 shoving in 2 and 0 as my terminals. 1 equals C times. So 2 goes in, which gives us 2 squared is 4. 4 divided by 2 is 2. So it's going to be 2, take away 0 goes in, and is nothing. 2C, C equals half. Okay, you can do those quite easily on the calculator. So we'll go Z times X between 2 and 0 dx. Solve SOLVE. 1 equals that for Z, please. Z is a half. That's how I do those quickly on the calculator. Okay, so now we need to find out the probability that the random variable is greater than 1. So probability that the random variable is greater than 1.5. Remember, that could be like that. It doesn't change anything. So the upper terminal was 2 from memory. Yep, 2. And the lower terminal is 1.5, or 3 on 2. Now, we found out the C value, so it's a half of x, or x on 2, dx. Okay, so antiderivative of that is power goes up and divide, which is x squared on 4, 2, and I'm going to convert this to a fraction, 3 on 2. 2 squared is 4, 4 divided by 4 is 1. 3 on 2 squared is 9 on 4. 9 on 4 divided by 4 is 9 on 16. So we've got 16 on 16. Take away 9 on 16, which is 7 on 16. It's always a good sign when you get your probability to be between 0 and 1. Don't know whether that's right or not, okay, in terms of an answer, but at least it's between 0 and 1, remembering that you can't get a value below 0, you can get 0, and you can't get a value above 1, you can get 1 though. Okay, so a probability between those is always a good sign. Alrighty, Ursula measures the length of time in minutes between successive incoming calls to a maths helpline. Whoa. And finds it is a continuous random variable with a PDF given by this. Find the probability to 4 decimal places that the time between calls is. So we're going to the calculator now. Okay, so let's go A. So the random variable is minutes. We'll go let x equal the number of mins, exactly 2 minutes. Time between calls is exactly 2 minutes. Right, so this one here, probability that the random variable is equal to 2 is integral of this one here. So I'm just going to say let g of x equal that function. So integral g of x dx between 2 and 2, and it's 0, okay? So you can't get the exact probability at that time, okay? It's got to be between values. So less than 30 seconds. Okay, so B, probability that the random variable is, so we're in minutes, so 30 seconds is half a minute. So x is less than or equal to, or just less than, a half. All right, so we'll integrate between a half and 0, g of x dx equals, and we're just going to do this on the calculator. So it's a half and 0, and our function is 0.6, shift 4 for e to the negative 0.6 x dx. So there it is, there in exact form. What is the approximation? 0.2592. Okay, C, more than 2 minutes but less than 3. So probability that the random variable is between 2 and 3 minutes. So it's 2 g of x dx equals, quickly change this on the calculator to be between 3 and 2. Okay, D, more than 7 minutes. So this is going to be slim, I'd imagine. So here we're going to go from positive infinity, because it's an e to the function, to 7gx dx. Okay, and we can do infinity on these calculators. So infinity is there, and 7 is there, and the calculator will know exactly what you're trying to do. 149 with 9 there, 150. Okay, E, less than 5 minutes given that it was more than 2 minutes. So E, probability that it is more than 5 minutes, X greater than or equal to 5, given that X is greater than or equal to 2. Okay, so this is going to be integral positive infinity 5 g of x dx divided by 2 g of x dx. Okay, so we're going to do 2 versions of it there. So integral to 5. So this will find out greater than 5, which is that one. And greater than 2 should be larger. And then what we're going to do is grab that and divide it by that. All right. Oof, another problem. Okay. Okay, so Alicia buys her candles from dusk. The length L of the candles she buys is a continuous random variable with this probability density function. So it's some sort of a quadratic, and I presume that if I integrate between 13.5 and 12, I'd get a total area of 1. Find the probability that a randomly selected candle has a length greater than 13 centimeters, given that it is at least 12. Okay, so let's go A. So probability that it is greater than 13, so L greater than 13, or greater than equal to if you want, given that L is at least or greater than 12.5. Okay, so to do this one, what we'll do is go, so 13, so our top terminal, actually I'll write this out. So our top terminal is 13.5, and we'll go to 13, and we'll call this f of L dl divided by this part here, integrate between 13.5 and 12.5. I'm running out of room here. F of L dl. All right, so let's do that on the calc now. 13.5 and 13, 8 over 225 times 27 take away 2x dx. So it's rather small, okay, which usually happens when you're at the top end of a PDF function, is that the probability between 13 and the top value, 13.5, is usually low. Not always. Anyway, and let's grab it again and do the smaller sample space, 13.5 and 12.5. So that's that. So we're going to do top divided by bottom. Quarter. I wonder if that would have worked out nicely by hand. It probably would have. Okay, B. At most 12.8 if it is less than 13.2. So probability that it's between 12 and 12.8. So 12 less than or equal to L less than or equal to 12.8. That means at most 12.8, so it can vary from 12 to 12.8. Given that it is less than 13.2, so L less than or equal to 13.2, or again, reminder that that can just be less than. Okay, so this one here, what we'll do is integrate between 12.8 and 12, f of L dL, divide by integrate between 12 and 13.2, f of L dL equals. Okay, so again, just use whatever we've done before. So 12.8 there, and 12 gives us that. Now let's rip that and do 13.2 to 12, and we get that. So it's this value here. So I'll make it 12 divided by this value here. Pretty high. Which kind of would make sense. Okay, we know it's less than 13.2. What are the chances between 12 and 12.8? All right, pretty high. Alrighty, so there is continuous probability. All right, so 15A allows you to explore that a little bit more. Good luck.